Welcome to this explainer. Okay, I want you to look around for a second. Look at a solid rock, maybe the glass of water on your desk, or even just look at your own hand. Have you ever actually wondered what all this stuff is made of? I mean, really truly made of at the absolute most fundamental level? Well, today we're tackling Unit 2, the composition of matter. And we're going to start by diving into the early thinking about this, tracing the greatest mystery in science from ancient Greece all the way up to the modern atom. It is a wild story of discovery that literally defines everything in the universe.
To kick things off, let's do a quick thought experiment. Imagine you're holding a block of wood, and you cut it exactly in half. Then you take that half and you cut it in half again, and again, and again. If you just keep dividing it, do you eventually hit a wall? Like, is there a physical stopping point where a piece is just so incredibly tiny that it simply cannot be cut anymore? Or, theoretically, could you just keep slicing it forever? Believe it or not, long before electron microscopes or modern labs were even a glimmer in anyone's eye, two heavyweights of ancient Greek philosophy were obsessing over this exact same brain teaser. We're talking about Democritus and Aristotle, and they came up with two entirely opposite answers to our little thought experiment. So let's break down this debate. Aristotle was the big champion of what we call the continuous theory. He argued that matter could be divided endlessly, forever, no limit whatsoever. He completely rejected the whole idea of microscopic building blocks and figured everything was just a continuous, smooth mixture of fire, earth, air, and water. Democritus, on the other hand, went the total opposite direction with the discreteness theory. He boldly claimed, no, there is absolutely a strict limit to how far you can break matter down. Democritus was convinced that if you kept cutting, you would eventually hit a tiny, solid particle that just couldn't be divided any further. He called these ultimate particles atomos, which is Greek for uncuttable or indivisible. Now, spoiler alert here, Democritus actually hit the nail on the head about matter being discrete. Those microscopic building blocks absolutely exist. But he made one pretty huge mistake. As modern science tells us, those atoms, yeah, they are definitely not uncuttable. Fast forward a couple of millennia, and we finally figured out that Democritus's supposedly uncuttable atoms actually have their own incredibly complex internal structure. They aren't just solid little bowling balls. Actually, an atom is much more like a miniature solar system buzzing around inside every single piece of matter. Right at the center, you have a tiny, super dense core called the nucleus, and that's surrounded by layers of what we call electron shells. And because we can break the atom down, we call the pieces inside it subatomic particles. Literally, the building blocks of the building blocks. So, packed into that dense nucleus in the center, you have positively charged protons and completely uncharged neutral neutrons. Then, zooming around the outside in those electron shells are the negatively charged electrons. And honestly, here's the craziest part of the whole shebang. Most of an atom's volume is just empty space. Which means the chair you're sitting in, the screen you're looking at, even your own body, is mostly made of nothing. Wild, right? Now, when you look at the properties of these subatomic particles, the scale differences are just mind-boggling. Protons and neutrons are the heavyweights. They sit right in the center, and both have a relative mass of about 1 atomic mass unit. But the electron? It is roughly 2,000 times lighter than a proton. Its mass is so incredibly tiny that scientists basically consider it negligible, like practically zero. That means almost 100% of an atom's weight is crammed right into that microscopic nucleus. But hey, don't let the electron's tiny size fool you, because it packs a massive punch when it comes to electrical charge. A proton has a relative charge of +1, and an electron carries a charge of -1. In its natural baseline state, an atom has the exact same number of positive protons and negative electrons. Because those opposite charges match up perfectly, it's a tie game. They balance each other out entirely, leaving the whole atom electrically neutral. So how do we keep track of all this? It actually boils down to a really simple mathematical blueprint that gives every element in the universe its unique identity. First up is the atomic number, which we represent with the letter Z. That's just the number of protons in the nucleus. And remember, since atoms are neutral, knowing the protons instantly tells you the exact number of electrons too. Then we have the mass number, represented by the letter A. Since we know electrons weigh practically nothing, the mass number is just a simple sum of the heavy stuff, the protons plus the neutrons. You can almost think of this as a secret decoder ring for the periodic table. Let's say you want to figure out exactly how many neutral neutrons are hiding in an atom's core. All you have to do is take the mass number and subtract the atomic number. For example, let's look at carbon-12. It has a mass number of 12, and its atomic number, meaning its proton count, is 6.
Well, 12 minus 6 leaves us with exactly 6 neutrons. It's just a wonderfully elegant, perfectly balanced system. All right. Up until now, we've been looking at atoms as if they're completely isolated, just floating around alone. But in reality, nature is incredibly social. The universe is not just some loose soup of single atoms. To actually form the complex matter we interact with every single day, the air we breathe, the coffee we drink, these microscopic building blocks have to start teaming up. So what actually happens when they do? When atoms join forces, they form what we call a molecule. By definition, a molecule is the smallest particle of an element or compound that can exist freely in nature. It's essentially a chemical squad of atoms bonded together. And what's really fascinating here is that these squads can be super simple, made of just one single type of atom, or they can be incredibly complex chemical mashups of totally different elements. And different elements actually have totally different personalities when it comes to this. Take neon, for example. Neon is a monoatomic molecule, mono meaning one. It is perfectly happy being a total loner, floating around all by itself. But then you have hydrogen, which is a little more clingy. Hydrogen naturally forms a diatomic molecule, meaning in nature you are almost always going to find it holding hands in pairs, as H2. But why stop at pairs, right? Atoms can form way larger groups. When an element forms a molecule with more than 2 atoms, we call it polyatomic. Ozone is a great example. It's 3 oxygen atoms, O3. Sulfur can literally form rings of 8 atoms, S8. And then we get to molecules of compounds, which is where the real magic of the universe happens. This is when entirely different elements combine chemically, like taking 2 hydrogens and 1 oxygen to make water, H2O, or nitrogen and hydrogen making ammonia, NH3. This infinite, Lego-like variety of combinations is exactly what creates the staggering diversity of matter all around us. Which brings us full circle to a pretty provocative thought. We started this explainer by looking at the early thinking about matter back in ancient Greece. Democritus was brilliant enough to realize atoms existed over 2,000 years ago, but he was completely wrong about them being uncuttable solid spheres. Science, by its very nature, is a relentless process of looking deeper. We sliced the atom and found the nucleus. We sliced the nucleus and found protons and neutrons. It really makes you wonder, what fundamental scientific facts that we absolutely swear by today might the next generation of scientists slice apart tomorrow? Keep questioning everything, keep exploring, and thanks so much for joining me on this explainer.